Hello everyone, my name is István Reguli and I'm going to present work with my colleague Gihan Mudaligay on modernizing an industrial CFD application. We are studying Rolls-Royce Hydra, an unstructured mesh production CFD code used by Rolls-Royce for simulating turbomachinery components, particularly things inside aircraft engines. It's been in development for over 20 years. It's written in Fortran 77 and consists of about 100,000 lines of code and has about 500 loops where we go across the mesh and perform some sorts of computations. Hydra is written in a library called OPlus, which targets unstructured meshes and parallelizes MPI. Our goal is to move this code base to the OP2 library, which is a successor to OPlus, and it enables MPI+X execution schemes and further optimizations. We didn't really have the option to do a by-hand conversion because the original code is in continuous development, and so we need to set up a continuous and automated process that is able to convert the current OPlus into the OP2 version. OP2 and OPlus build on the same fundamental abstraction for unstructured meshes. First off, you have sets such as nodes or edges. Then you have maps that associate elements of sets with each other. For example, edge 10 connects to nodes 3 and 7. And then you have data defined on sets when one or multiple values are defined on each set element. So for example, you could have x, y, z coordinates defined on each node. Then an operation is expressed as a parallel loop over all elements of a set, accessing data defined either on the set and through mappings on different sets. So for example, in this little example, we collect data from each edge, called EWET. We gather data indirectly from nodes called X, and then once we perform some computations, we indirectly increment data on nodes again through this edges to nodes map. This parallel loop looks like this in code using the OPlus API. We have height bar loop where we describe what set we are iterating on. We list the data sets that we are going to access, how we are going to access them in terms of reading or writing or updating, and whether we are accessing them directly or indirectly. And then in that code we do a for loop iterating across a range of edges, accessing the mappings and then performing the calculations and basically directly reading and writing to our data arrays. In contrast, OP2's API looks like this. We have a very similar OP par loop construct, which explicitly lists what set we are going to iterate on, what data sets we are going to access, whether directly or indirectly through a mapping, and whether we are going to read or write or increment them. And then we provide a function pointer to edgewall, which describes the operations that are to be applied to each and every element. The key difference between OP2 and OPlus, other than OPlus only being able to do distributed memory parallelism, is that OP2 achieves by design of its API a separation of concerns, meaning it separates the description of what to compute from actually how to do it. It basically comes down to OP2 having to feed the per element kernel and then take the results the per element kernel gives it. And then, given this, OP2 is free to organize both parallelism and data movement. So with the default implementation, we do have a generic execution for the OP par loops, but then OP2 can do source-to-source translation. it basically uses Python scripts and string manipulation to look at the description of an OP par loop call, parse the arguments, and then depending on what form of parallelism is targeted, it will generate boilerplate code to feed this per element kernel. And then depending on what we do, it will arrange parallelism, it will manage race conditions, it will manage reductions, it will manage transfers between different memory spaces, and even manage data layout conversions. So how do we actually do this conversion? First off, because both libraries fundamentally use the same abstraction and the same data structures, in a special case, namely running on a single process, these libraries are actually interoperable, which greatly simplifies the conversion process because we can convert loop by loop and check for correctness. The first step in the conversion process is making sure all per element operations are outlined into separate subroutines. This is already done for most loops, but for a few, especially smaller ones, these were still left in line. And so we strip these out, place them in separate routines, and replace them in the original loop nest with a call to this subroutine. Step 2 was parsing the existing OPlus loop structures and then replacing them with an OP parallel loop call. Again, thanks to strict coding guidelines and Fortran 77, we could do this using essentially regular expressions. So in Python we wrote a script which reads in the code on the left, which is the parallel loop in OPlus. And it looks for all the data sets, the mappings, and then how and what arguments are passed to the per element kernel. So for example, for the first dataset EWT, we notice that it's accessed directly on the set edges. We notice that it's read-only, it has 3 values per set element, and then it is the first one to be passed to our edge wall outlined per element kernel, and so we put this as the first argument to the OP par loop, OP arg that, EWT, the access directly size of 3, uses double precision and read only. Then the next argument is X. X is accessed indirectly through the mapping NE, so the edges to nodes mapping. It is the second and third arguments to edge wall with the different map positions, the one end and the other end of the edge. So we put the second and third in the OP par loop, and so we keep on doing this for all the arguments, and then whatever is left are data sets that are iteration invariant. In our case, this frac variable, which then is passed as an OPR global, and OPR global is data that does not depend on what set element we are on. So with this, we were able to convert actually without significant issues virtually all of the OPlus parallel loops to use the OP2 API. The next step was to manage global constants, global scope constants. Hydra uses common blocks for this, and within the parallel loops themselves, plus these are actually read-only, and most of the times these are included using a simple preprocessor hash include. For the CPU targets, we could actually have left these as common blocks, but for CUDA Fortran we can't do that, so we needed to move all of these to a Fortran 90 module, which again is a fairly trivial exercise in string manipulation. We just pull all of these into a module, and then to support CUDA we basically duplicated each of these constants, added a suffix, and then put them in the GPU memory space using the constant or device qualifiers, which are of course only enabled if we compile for CUDA. And we also added an OP const subroutine, which when requested will upload a given global scope constant from the CPU to the GPU. Then we modified the code in Hydra and looked for all uses of these common blocks and replaced them with the use of the new Fortran 90 module. And then finally we looked over again the whole code, again with simple text processing, looking for occurrences where these variables are modified or updated, and whenever we find something on the next line, we insert a call to this OP-const, thereby uploading this change to the GPU whenever the GPU is being used. This of course does result in repeated updates in some cases, but this does not affect correctness or performance as it turned out. Now that our application is converted to use the OP2 API, we will use the source-to-source translator written in Python to spit out converted application files, which now, instead of using the generic OP par loop implementation, use the platform-specific optimized application files. These can then be compiled with the ordinary compilers for that platform, linked against the OP2 backend libraries to get the platform-specific binary executable, which then can be combined with the parallel I/O capabilities to be run on the hardware of our choice. As I mentioned, OP2 supports shared memory parallelism, but in this situation we need to avoid race conditions when, for example, multiple edges want to increment the same node. To do this, we have three key strategies. First off, we have global coloring, where we color all the edges with respect to the common nodes, and then execute edges of the same color in parallel. Unfortunately here, memory locality is going to be poor because no common nodes are executed or read or written when executing edges of the same color. We can also do a hierarchical coloring, where we group edges into blocks and then color blocks themselves, and then these blocks can, for example, be assigned to different OpenMP threads. With CUDA, where we have a second level of parallelism, we can further color inside of the blocks too, to avoid race conditions between CUDA threads. This gives much better memory locality, but more synchronization on this second level of elements. And finally, depending on the platform, we actually can use atomics to perform these indirect increments, which do offer very good memory locality, but some platforms either do not support it or the throughput is fairly low. Generating the boilerplate for MPI+ sequential and MPI+ OpenMP is fairly simple. You just pass the reference to the data on the current element and execute the coloring scheme with OpenMP. With MPI CUDA, we need some further parsing and modification of the per element kernel, because we need to look for global constants and modify them with the OP2 constant suffix to access the constants in GPU memory space. Then, if the array of structures to structure of arrays conversion is enabled, then we need to look for array indexing of particular arrays and convert their access pattern to an SOA scheme. When using atomics, again, we need to look for certain array accesses, find the additions, the increments, and swap the expression for an atomic add call. The process is not terribly complicated because we know which arguments we are looking for, where we need to perform this conversion, well, either conversion. and then we parse the formal parameter list of the subroutine and use regular expressions to replace occurrences in the implementation. And we can actually do this when these per element subroutines call further subroutines. We can propagate this information through. Performance we can see when we compare the original implementation, the implementation where the rest of the user subroutines are outlined, and the OP2 version is that performance is on par with the previous version and sometimes even slightly better. Depending on what partitioner we use, we get slightly better or worse performance. We also look at strong scaling on the UK's national supercomputer called Archer, which is a Cray XC30 machine with Intel Broadwell CPUs. We can see that OP2 Hydra scales significantly better than the original Hydra with OPlus. This is because a better optimized MPI communications scheme. On a much larger problem, we actually scale up to 24,000 cores, and again we see OP2 Hydra performing on par or slightly better than the original OPlus version. And finally, on GPUs, we tried the various execution schemes, mainly on the V100 GPU. The global coloring was actually outperformed by the atomics. The atomics proved to be fastest on the V100 GPU. They ended up being about 3 times faster than the original code on a Cascade Lake dual socket machine. How do we make sure this OP2 version gets adopted over the prior OPlus version? First off, this project is part of a larger UK project that aims to do full coupled engine simulations, and so we are first working closely with other academic institutions and partners to run these really large test cases using OP2. And then of course Rolls-Royce Hydra itself will hopefully adopt this version for production use as well. To be able to do any of this, we need to support the parallel development of these two versions, because OPlus version is still actively being developed. Any updates need to be quickly brought over to the OP2 version. This is largely possible because all steps except for the first one where we outline the loop bodies is automated, but thankfully there are fairly few of these, and we have been pushing these updates back to the original version. And of course, to convince everybody that this is useful, we need to show even more convincing performance and further features. We are currently working on further MPI communications optimizations, advanced CPU vectorization, and things like automated checkpointing and recovery. In conclusion, we have taken an industrial CFD code written in Fortran 77, which only had MPI parallelization, that is also in continuous development, and developed and streamlined the process to convert this legacy version to a modernized version. Some changes still have to be adapted in the original OPlus reference implementation, but largely we can get away with using scripts and text manipulation thanks to the simplicity of Fortran 77 and coding standards. Using this method, we have modernized this code to use the OP2 library, which enables MPI+X execution schemes through source-to-source translation and allows the experimentation and the deployment of various optimizations and improvements. We have demonstrated performance to be on par or even better than the original OPlus version, and through support for CUDA Fortran, for example, we have shown 3x speed up compared to state-of-the-art CPUs on an NVIDIA V100 GPU.